All right. Yeah. My name is Kevin Doherty. I'm a research engineer at Boston Dynamics, working on the Atlas team. So for the past year or so, I've been working on getting the Atlas humanoid robot to more intelligently manipulate objects, and a big part of that has been what we're calling here KFC fusion, which is cooking up kinematics, force, and camera data for object state estimation. So a big thank you to the organizers also for having me here to give this talk. On a personal note, this is like my first talk since I've joined Boston Dynamics that I've gotten to give publicly for a conference about some of the work that I've been involved with. So this is really exciting for me. Oh, there we go. First, a little bit about Boston Dynamics. We've been around for 30 years now. We were founded at MIT in 1992, and for the past 30 years, we've been developing mobile robots of various kinds. In 2021, we were acquired by Hyundai, and we've grown now to over 500 employees. I think actually since I started, this may be a little outdated now, I think we're now over 700 employees, and we're always hiring. So it's been a very exciting time to be working on robots and growing quickly. Just to give a little overview of some of the robots that we have at Boston Dynamics, our three primary robots are Spot, or quadruped robot, which many of you will be familiar with. It's an autonomous data collection and inspection robot primarily. We have Stretch, which is our wheeled mobile robot. It's primarily used for warehouse automation. And then, of course, Atlas. This is our new electric Atlas robot, which is our humanoid platform that we've been using most recently for a lot of cool manipulation stuff. As I said, this is our electric robot. Most of the stuff that I'm going to talk about in this talk is going to be dealing with our previous version of Atlas, the hydraulic Atlas robot, but many of the sort of manipulation skills will transfer over to electric Atlas. In particular, I want to focus on some of the sort of different technologies that went into this video that was recently released, called HD Atlas Manipulates. And this is kind of a montage of some of the different manipulation skills that we've developed for Atlas. So you can see like pick and place of some of these large objects, lifting kettlebells, which we'll see a lot of, doing things like object reorientation, more fun pick and place stuff. This is a fun one. This is regrasping an object, which is particularly tricky. Obviously, dancing is a big part of what we do. We're particularly interested in lifting heavy and inertially relevant objects with Atlas. That's one of the kind of the key capabilities that we're developing. So here we're lifting like a big exhaust pipe. Here's we have a heavy tool bag, and we want to retain our ability to do dynamic locomotion. Here's a little bit more like pick and place of some heavy car parts. So this is a strut for an automotive strut, which is I think around 7 kilograms or 8 kilograms, something like that. This is a wheel, which is around 10 kilograms. So the robot actually needs to like reason about how heavy these objects are in order to balance as it's moving around, which makes this particularly tricky. Here's another kettlebell. So Atlas is always getting a good workout. And then at the same time, we also want to be able to manipulate some kind of delicate parts, right? So here, this is a plastic engine cover. So I want to go into a little bit, some of the kind of the technical details of what went into some of the behaviors that are in that video that it's easy to sort of not notice as they're going by. So in particular, we've been developing new technologies that support things like regrasping, like we saw earlier with the strut, but here it is with the compressor. Picking and placing objects with external support. So this is particularly tricky, reasoning about how much of the object's weight is being supported by external fixtures rather than by the robot itself. The robot needs to know how, what's going on in terms of the mass properties of objects. And then, of course, doing dynamic locomotion with an object, one that is heavy, requires the robot to reason about how it balances in response to this inertial load. And now the focus of this talk is going to be on object state estimation. But first, I want to give a little bit of an overview of how Atlas works from a control standpoint. And so the sort of workhorse technology that gives Atlas its athleticism is called Model Predictive Control, or MPC. I expect many of you will be familiar with this, so this might not be very new, but for those of you who haven't seen MPC before, the basic idea is that Atlas is continually replanning a near future trajectory in a moving horizon. Starting from its current state, it's going to use online optimization of some objective function with respect to the constraints relating to Atlas's dynamics and kinematics. And we're going to track the most recent solution trajectory. So this is what that looks like. You can see Atlas is predicting a future horizon of the different kinematic states that it needs to go through. But of course, this requires a model of the dynamics, and this is sort of the blessing and curse of model predictive control. The fidelity of your model matters a lot for the performance of the overall system. And of course, everything that goes into this involves like nonlinear dynamics, costs and constraints. And so you can iteratively linearize and solve, but you need a good model of the system. Now, to make this work for manipulation, we wanted, in particular, as I mentioned, to manipulate objects that are heavy enough that their momentum actually matters while retaining dynamic locomotion ability. We don't want to just compensate for this inertial load on the object, but we actually want to be able to exploit it as we're moving around. And we want to do this in a kind of generative way. We don't want to have canned trajectories for specific objects because we want some hope of this actually scaling, right? And of course, we'd like to provide only kind of a high-level task specification rather than having to give the robot all the details. So here, an object reference trajectory will guide what the robot should do, and the robot can figure out how to affect that change on the object based on kinematics based on the kinematics and dynamics of that whole system. Now, in a little bit more detail, what that looks like is that we take a sort of typical model of our robot's momentum dynamics and kinematics, which you can see kind of on the bottom here. And we augment that with a dynamic model of the object. And it's very simple. Essentially, we just say the momentum rate of change is equal to the net wrench on the object. And then we add pose and interaction wrench constraints between the robot and the object. And using this, we can simultaneously optimize online the robot and object motion. And what that looks like is this video here, where you can see we are predicting a future horizon for the object states. Okay, and this works really well. So MPC with an object model has powered a lot of our developments over the last 2 years, and it's enabled us to do lots of cool stuff like dynamic locomotion, which you can see here, where we are picking up this this exhaust pipe. I think this is also around 7 kilograms or 10 kilograms in that range. And we can do parkour with it, which is super cool. The same sort of pick and place that we saw earlier. And then even like pretty cool behaviors, I think, like throwing an object. Here we're throwing a heavy tool bag to a desired target location. But of course, in practice, when we run this around the lab, things go wrong all the time. So we see things like this, where we miss a regress, we drop an object. We go to place a kettlebell, and we just totally miss and drop it on ourselves. And this is my personal favorite. Every now and then, we'll pick up an object, we go for a grasp, and the robot just totally falls over. Okay. So what went wrong? So the key thing about this MPC with an object model kind of idea is that we require some idea of where this object is at all points in time, right? We need to know the object's state in order to have some idea of its dynamics and kinematics. And this is a huge drawback of that approach, because in every one of those examples that I just showed, the robot thought the object was somewhere that it was not, and that caused it to miss grasps. And occasionally, because it's thinking about the momentum of the object that it's about to grasp, it will miss and then just fall over. We don't want this. What else could possibly go wrong? So here I'm showing 2 videos. These are simulation videos of eAtlas, and I hope it will become clear why I'm using simulation in a moment. But here on the left, I'm showing a video where the robot's about to pick up this kettlebell. I'll give you a little primer on what's about to happen. And it's been told that the mass of this kettlebell is much less than the true mass. So it's not expecting much mass of the object. And then when it goes to pick it up, let's see if the video loads. Immediately it gets thrown off balance and falls over. And then here, we do the opposite. We tell the robot that the object to expect a really heavy object, and then it doesn't have time to react to the fact that the object is actually much lighter than it expected. And so this is kind of the second drawback of this approach, which is that if you want to know your object's dynamics, you need to know its inertial properties. You need to know how heavy that object is. And so for MPC to work well in these settings, we need to know the mass properties of the objects that we're dealing with. And in many of those examples that I just showed, we did know the mass properties of the objects. So that helps a lot. But I want to talk about how we can kind of relax some of these assumptions or just do better in general and have a more robust manipulation system on Atlas. Okay, so I want to first deal with this issue of object pose estimation. And these are sort of the ingredients that we have on Atlas. So we have two primary sources of information. The first is forward kinematics. And the essential idea here is that if we assume that the object is in a fixed pose relative to the end effector, then we can just use the robot's forward kinematics to say, okay, the object is stapled to my end effector. However my end effector moves, that's how the object moves. This is a high rate signal, which is great. You don't need to be looking at the object to know where it is, which is also great because oftentimes we're carrying objects that are only in partial view, they're occluded, or they're just out of frame entirely. But the downside is that we have no way of knowing when or how an object has moved relative to the end effector. So this is a problem for two reasons. One is that when we're not trying to affect motion of the object in hand, it often happens accidentally. And the second is we have no way of actually commanding the robot to like move an object in hand if we wanted to, which is particularly challenging. The second source of information that we have is a vision-based object pose estimator, which is a trained neural network. It's comparatively slow in comparison to forward kinematics, runs at about 10 hertz, and it's time delayed relative to our control system, which is also not ideal. It can't deal with occlusions or out-of-frame objects, but it works very well when objects are clearly visible. So you can see this working in this video. We're essentially giving the object pose estimator an initial estimate for the object pose, and it's giving us back a refined estimate, and we run this continuously on the video feed from the robot. And so the essential idea here is that we'd like to combine these different sensing modalities, this learning-based model of object poses, and this more traditional model of forward kinematics to do better. And this is kind of our recipe here. So the idea is that we're going to use forward kinematics, but allow the object's pose relative to the end effector to change over time. So we'll see the object pose estimator with our current track pose estimate, and then propagate its vision updates to the end effector frame. And then MPC will assume that the object is glued to the end effector at the latest end effector relative pose and use that to plan forward in time. And we're just continuously updating that state. So what that model looks like at a high level is what I'm showing here on the right. We track separately these world frame object states and end effector frame object states. And then over time, we track the end effector frame object state by essentially saying at each point in time, the end effector relative object state is approximately the same as it was in the last state. And then these visual pose estimates propagate from world frame to end effector frame. We also require that this happens in real time. So how do we actually do that? And at the same time, we need to deal with the fact that these sources of data are coming in asynchronously. The way that we handle that is with something called a factor graph. And these are a particularly natural modeling tool for these types of problems. There are many convenient open source tools for working with problems that are parameterized by factor graphs, like GTSAM series and G2O. And if you haven't seen a factor graph and you're not familiar with this, then you can really just think about this as a way of writing down a particular optimization problem here. So what we're looking at here is an optimization problem whose state variables that we're trying to estimate are these big labeled circles. And then the cost terms or residuals that we're trying to minimize are these filled in dots. And each one of those cost terms has edges to all of the state variables that it relates. And so the benefit of these factor graph models is that it's really easy to model new state variables and measurements, and this simplifies the sensor fusion problem. But the drawback is that this graph is going to grow every time we add new states to the problem and new measurements. And this makes it challenging to do real-time inference. So instead, what we do is we use something called a fixed lag smoother, which keeps a factor graph that has a bounded window or a bounded history of states, and then marginalizes outside of that window. You can think about this as kind of a generalization of an extended Kalman filter, where instead of just keeping the most recent state, we keep a buffer of previous states. And what this allows us to do is that when we get visual pose measurements that are sort of old relative to the time that the controller thinks it is, we can link those measurements up to the correct frame and time that they came from. Now, to kind of like break down how that model that I showed earlier works into a factor graph, this is 4 frames of motion of the robot as it's picking up an object. And you can see that at the moment that we pick up the object, we have a prior on the end effector relative pose of the object. And this is just based on where we thought the object was at the time that we graphed the object. And then we have these relative measurements, or relative, the model of the relative change in pose for the object in hand, which is essentially just a random walk here. And so what we're saying is that in expectation, if we don't have any other information, then the object remains in the same pose relative to the end effector that it was in before. But if you do have like a forward model, for example, if you were saying, if you had like a learning-based model, and you could predict how you wanted to affect an in-hand change, this is kind of the place where you would insert that information. The measurement that, or the model that links the end effector relative pose to the world frame pose of the object is just the forward kinematics of the robot. Essentially, you just concatenate these transforms and you should get the pose of the end effector. And then finally, visual pose estimates, when they're available, come in as measurements of the world frame object pose, just by way of knowing where the camera is in the world. Now, incorporating vision data turns out to still be kind of tricky. So the model that I was describing earlier, where we send the track pose to the pose estimator is kind of depicted here. We put this together and then we tried it on the robot, and immediately it looked something like this. Let's see if the video loads. There we go. Okay, yeah, so this was like the first time that we deployed this. So what went wrong? You can see what happens on the right here. In green, we get a bad pose estimate. This causes the object to go out of hand in its track. Since we're operating in this regime where we send the tracked pose back to the object pose estimator as an initial guess, the object pose estimator can't refine that pose anymore, and this whole system goes unstable when we drop the object. So robustness is really important for this. Otherwise, we're just going to be dropping objects all the time. Fortunately, when the system works, it works quite well. So here you can see the kinematic track in red compared to the fused track in blue. And you can see like the blue tracked object is much better than from kinematics alone. But we need to know, in order for this to work well, when the neural network got the right answer without actually knowing the answer. Because of course, if we just knew where the object was, we'd be done. A natural thing to try here, and a thing that we did try, is to essentially just ask the neural network to score itself, right? But of course, this is environment dependent, lighting dependent, background dependent, and often this works about as well as just the pose estimation in the first place. So what we use instead is this geometric self-consistency measure, which is common in pose estimation literature. And essentially, we seed the neural network with multiple initial poses, and then it gives us back multiple answers. And then we evaluate the consistency of those poses on the way out. And if they're consistent, we say it's more likely to be an inlier. Still, these measurements could be biased. And so we check also whether or not the predicted pose could correspond to the object being in hand, or if it's out of hand, then we reject that measurement. Okay, I want to talk briefly about how we add in mass property estimation. So here, we just kind of mirror what MPC does, where we augment our model with this net wrench is approximately equal to the momentum rate of change. Here, rather than in MPC, where we're trying to compute the desired wrenches to affect a momentum rate of change, we're measuring wrenches and we're trying to determine from the momentum rate of change what the mass properties of the object are. So we add these new states, the mass and center of mass. And we get object velocities and accelerations estimated from forward kinematics. And then we measure wrenches from the wrist force torque sensors and joint torques. And then we say that the object frame mass properties should be approximately constant over time. The nice thing about the factor graph representation is that it allows us to develop an estimator that is very modular, right? We can just essentially staple on this mass property estimation module to the kinematic state module that we had before, and then we can use exactly the same inference approach that we had. And so putting it all together looks something like this. We can do all of those same behaviors that I showed earlier, but without prior mass properties. And so here you can see us doing regrasping of the strut. And here you can see some pick and place of the kettlebell. In all of these videos, the object is colored by the mass. So you can see that it starts out blue, which is like low mass. We initialize this to like 100 grams just to make it do something interesting. And then as we pick it up, we quickly converge to the correct mass. And then here you can see, this is one of our manipulation test stands. This is a spot arm with an Atlas gripper. We can pick and place this kettlebell, and every time the robot picks up this kettlebell, it has no idea how heavy it is. It just thinks it's 100 grams. It has to estimate from joint torques how heavy the object is. Another benefit that's kind of hiding in here is that we also added a pre-grasp tracking module, which is all done through the factor graph. And so once again, you can just sort of like staple this onto your factor graph, and it works quick. Okay, so key takeaways here. MPC benefits from accurate state estimation. In fact, it often fails if your state estimation is goes wrong. Here, we're enabling that by using sensor fusion between traditional modalities and learned models. In fact, we get a key benefit of modularity from the use of factor graphs here, but there are a lot of things that are still challenging. So like perception, we don't know when to trust perception models and how to reject outliers. The use of traditional sensing modalities was a key sort of enabler of outlier rejection here, right? The fact that we know that there's something that should be geometrically consistent about the task that we're working with allows us to reject outliers from the neural network, but it also means that we have to make some modeling decisions. And so we have to trade off between how much we should model and the generality of the system. Because obviously in practice, a lot of our assumptions end up being violated. Observability is a big challenge with these kinds of tasks. So often we have unsensed contact, we have incidental collisions with the environment, and these things particularly affect like how heavy the robot thinks that an object is. If you bump an object, that force is not accounted for in the model. So there are a lot of things that are still kind of interesting to work on. And I'll say quickly, if you want to work on those things with us, we're always hiring. You can check out bostondynamics.com/careers to check us out and to apply. And with that, I'll take any questions.
So we have some time for 1 or 2 questions.
Yes.
What I'm fascinated. I would love to know how are you dealing with actual contact sensing using your joint codes. You have crosstalk sensors in the wrist, I assume, right? And you said you have bones even Kinematics to detect slippage. That's what I don't want to slides you saying that's a hard part. So are you thinking about what are you thinking about in terms of contact sensing, and what do you think we're actually driving with?
Yeah. Very hard. Right now, we do things in a very naive way, which is almost like sort of open loop. Like we plan to grasp, and we kind of assume that we've grasped when we grasped. We assume that we have grasped when we plan to grasp. We have some like very naive heuristics that rely on like joint angles and things like that. But it's a very naive system. We're looking at tactile sensing, which I think would be really helpful. Also, like would help us get around some of these observability issues, because kinematically, like I said before, we have no way of observing slip, except if, like in this current system, in order to observe slip, we need the robot to get the object into view of the camera. And ideally, you don't have to do that. Ideally, you can feel that the object is slipped in hand. So things like tactile sensing, I think, would be really useful there, and would also simplify our like grasp detection or our contact detection.
Any more questions?
Yes, thanks for the impressive talk. I'm not very familiar with the MPC approach, so I have maybe some stupid questions, but I want to, you to clarify. So first of all, is this approach assuming like every object you are known and with like CAD model? Yes. Okay, and the second question is, like when you lift the one up, why don't you just use simple like a positional control instead of MPC? I don't think that matter mass properties matter so much for that. And my last question is to achieve a generalizable mobile pick and place. Do you think like what do you need to do to extend your approach? Yeah.
Yeah, those are a lot of good questions. For the first question, yes, we assume that we have a model of the object. So the visual pose estimator that we have uses a render and compare method. So we render the CAD model and then use like the neural network to predict how we should move the CAD model to align with the image. We also use that to derive other, previously we used that to derive inertial properties of objects, like assuming constant density, things like that. So the first question, second question was about using position control. We've been thinking a lot about position control recently, and we have some results about doing that. I don't have anything in my slides, but yes, that is a thing that we do also, and it works pretty well. But that's relatively recent that we started doing that, I should say, like within like the past year.
Is the problem of the existing approach of maintaining balance?
Yes. Yeah. Yeah. So one of the things that we've been doing more recently is using impedance to pick up an object, and then from there, if you look at the object, you can initialize where that object is in hand, and then you can start doing tracking if you want to do something like fancier like this. But yeah, this is totally compatible with doing those kinds of control methods. Sorry, what was the last?
How to extend this?
Oh, yeah. Yeah, I wish I knew. I mean, that's like the $1 million question, right? Ideally, there are a few things. So doing away with mass properties was huge for us because now we can just pick stuff up. It's also like a key technology for interfacing with teleop, which has been huge for things like imitation learning. I think like learning has to be like, it seems like learning is going to be a big component of these systems for generalizing, for being able to grasp a wider variety of objects without having to know in advance how you're going to manipulate them. That seems big. Perception is, I think, going to be remains a big challenge. I think like when you go into new environments, like it's very different from the sort of tabletop manipulation setting where you can have a relatively consistent environment. If you're like operating in like a warehouse or a factory, the scene could be very different. And most of our perception technologies are based on learning, and it can be very hard to know when those things are going to be reliable. I'm like a personal advocate of like having physical models, having other traditional sensing modalities that you can use to check your learning models against in order to improve robustness. So I think those are all like things that might help, but yeah, obviously I don't know. I wish I knew the answer, like I said.
Thank you.